So the last piece we want to talk about in section 7.3, there are some product formulas and also product to sum. So what we're looking at is things like sine x plus cosine x, or maybe sine x times cosine x. And can you convert something like this, a summation, into a product of sines and cosines, or converting a product like this into a sum of sines and cosines? And there's a number of ways to do this. They can all be derived from earlier formulas. Really, once you know the Pythagorean identities and those sum and difference formulas that we did a couple of sections ago, all the rest of these, the proofs are very easy to follow and they're laid out in your text. So I was just going to show you one of these. If we started with sine of u cosine v. So sine and cosine are taken of different values, and I want to find a way to write this as a sum. Well, there's a couple of things that we can do that allow us to manipulate this. One is to go back to our addition formulas and note that sine of u plus v is equal to sine u cosine v plus cosine u sine v. And this has the sine of u cosine of v that we were looking for. Now similarly, if I do the difference formula, sine of u minus v, I get sine of u cosine v minus cosine of u sine v. And that works out really nice because I'm just going to take these guys, add them together. So that works out to sine of u plus v plus sine of u minus v equals, now when I sum these up, I've got 2 sine of u cosine of v, but these two are the same terms but with opposite signs, so that goes away. So now I've got 2 sine of u cosine v, but it was just sine u cosine v I was interested in. So I can solve for that. Sine of u cosine of v, sine of u plus v, plus sine of u minus v, all over 2. And that's one of the product to sum formulas that we can use. There's 4 different ones involving sine and cosine when they've got the same variable, sine and cosine with different variables, cosines and sines multiplied together. And there's also sum to products that can be worked out similarly. I wasn't going to do one of the proofs of one of those, but I think I'll show you just an example of what it starts to look like. So I can start with the last one, where we had sine of u cosine v equals sine of u plus v plus sine u minus v all over 2. And if we do a little switch of variables, so let u equal x plus y over 2 and v equal x minus y over 2, and you get u plus v equals x, and u minus v equals y. So substituting those in for all the u's and v's up here, I get sine x plus y over 2 cosine x minus y over 2 equals sine of x plus sine of y all over 2. So sine x plus sine y equals 2 sine of x plus y over 2 cosine x minus y over 2. Now you notice I put these in parentheses here and here because I wanted it to be very clear. This is an argument of the sine function, this is an argument of the cosine function. This too does not cancel with any of that stuff down there. These are acted on by the sine. It's not all multiplication, so cancellation does not occur. But this would be an example of a sum to product formula, and we can derive it from the product to sum formula that we had previously. So I'll give you an example of how we might use this to prove an identity. Sine 3x minus sine x over cosine of 3x plus cosine x equals tangent of x. Now, if you happen to have worked out the triple angle identities and you have those committed to memory, you could use those here and here. But we can use sum to products for both of these and see what happens. So if I start with what's on the left and I replace both the numerator and the denominator of this expression with the equivalent sum to product formula, again, I derived the one previously. There's a table of 8 of these that's listed in your textbook, so that's where you should be going to reference this. But we end up with, if I replace the numerator with the appropriate sum to product formula, I get 2 times the cosine of 3x plus x over 2 times the sine 3x minus x over 2. For the denominator, I'm left with 2 cosine 3x plus x over 2 times the cosine of 3x minus x over 2. But we get some nice simplification. This is 4x over 2, which is just 2x. This is 2x over 2, which is just x. So I'm left with 2 cosine of 2x times sine of x over 2 cosine of 2x cosine of x. Now I can cancel. 2 divided by 2 is 1. Cosine 2x divided by cosine 2x is 1. Sine over cosine is the tangent, by definition. So we get a nice identity out of it, too. So just another tool in the toolbox. Our toolbox is getting pretty expansive at this point. We've got the Pythagorean identities. We've got the identities that came from the reciprocal identities, your book called them, that came from the definitions of the trig functions. We've got addition and subtraction identities. We've got double angle identities, half angle identities, now the product to sum identities. So our toolbox is getting pretty deep. You should be keeping track in your notes of all of the different formulas that your book is giving you, so that as you're working through the homework, you've got those ready as a quick reference and you can start committing them to memory. So the next sections, we'll be looking at some trigonometric equations that we want to solve, and a lot of that's going to involve applying the appropriate identity.